Let's get started. We're talking about Bayesian networks. So just to summarize, let me probably summarize everything that we've seen thus far with a quick example similar to the examples that we saw in our last lecture. And then let's talk briefly about a couple of extensions or applications of all this before we turn to Markov models, okay? All right, so remember that Bayesian network is it uses a directed acyclic graph. So imagine that you have, as we had in our last lecture, a very simple problem. Let's say that the problem is for me to determine, say, a medical application for a change. How about that? That my goal is to determine whether you have an infection or not, a viral infection, and if it's a viral infection, which of two potential viruses that could be, okay? So we start with defining our problem, and that's where these graphs are helpful because we need to define a probabilistic model, and define a probabilistic model is not easy. It's not an easy task, so we want to use as many tools as we can to do so. So we can think about the problem. I have, say, virus A, and I have virus B, right? So I have these two viruses. And the way I'm going to measure whether you have an infection or not, let's say that I measure whether you have fever, right? Or I could measure whether you have a throat or whatever, right? Whatever it is, let's say fever. So I have these three variables, right? And I know that virus A increases my fever or your fever, and virus B also increases fever. Now, a priori, virus A and B are independent, and we know this because if we apply the techniques that we have discussed here in class, these two are inseparable, right? Correct? But now let's say that I observe a fever. So that means I measure your fever, and I now know that you're running a fever, right? So this is my observation. So now you're running a fever. And then I want to test whether it's, say, virus B that's causing this, right? So I run a test. I do have a way to run a mouse swab and then put it into a machine. And it says that you do not have that virus, right? But what happens is when I do this, then something very interesting happens, right? Which is that these two variables, the random variables that were inseparable, now they're no longer inseparable, right? Because I'm blocked, so to speak, the path from one to another, because I know that I have fever. I know that I don't have virus B, hence the probability of virus A has to have increased, right? So I can say that these two are now disconnected. I can say that. That's the same, obviously, to state the obvious fact that we know by now, that having virus A, say, will be a function of virus B, right? Whatever that function f is, it's probably unknown to me, but there is a relationship between these two. If these are the two only possible viruses that can give me fever, right? There's no other possible way for me to get fever, right? By being in a warm environment or what have you, right? Being what have you. Then, well, then 1 minus b, right? Or 1 minus the probability of b. The probability of A would be 1 minus the probability of b. And so on. I could complicate things a little bit further, right? So let's say that I have my virus A, my virus B. I have my measure of whether you're running a fever or not, but I also have a variable which is aspirin, right? So again, these two are inseparable, right? But let's say that I measure fever and you're running a fever, you're not, running a fever. That could mean that you, or that would imply in this model that you don't have any virus infection. But what happens if you took aspirin? And we know that aspirin reduces your fever. Whoops, right? So unless I observe this, I still don't know, right? So it doesn't matter whether I observe this or this, right? It really doesn't matter because I don't know whether you've taken aspirin or not. And that does have an effect on fever, okay? So this is very important when you design these models because if you don't know all the variables that define your physical world, which is usually the case, right? We usually don't have all the details of how our world works, or the details are just so complicated that we simplify the model. Then we end up with a result that has a very well-known term, which is called bias, right? We have a biased result, right? And you hear this in the news all the time, that this result did not include elderly people, or it only included healthy people, or it didn't include enough minorities, or it didn't consider any minorities, or what have you, right? It only considered people in certain parts of the country or the world, or when the climate was good. You have to account for all the variables, otherwise your results are going to be biased by those variables. So that's what happens here. If this is a real model, but you're working with this model, then you're going to have biased results. Okay. So you see how this works. This just to give you an idea of how these things work. You can move these a step further, these Bayesian networks, and apply them to determine causality. Now, until now, we have defined algorithms that compute basically the probability of, say, a variable y given a variable x, right? We have this conditional probability. That's the way we have modeled of, most recently, our projection from an observation x to an expected or outcome y, right? This is so typical of machine learning. In more general terms, as we've said many times, we're going to consider the general function f of x equals y, where y is our output and x is our input feature space, right? This is really cool, but that only allows me to determine correlations, basically, right? And we've talked about this, or probability, so we can talk about linear correlations, nonlinear correlations, and we've talked about these two. We have talked about independence. We've talked about probabilistic relationships, right, with Bayes and other methods. So this is cool, but that does not mean causality, right? So how do I move from this to causality models? So let's go back to the example of the aspirin, right? Let's say that you're running a fever and you take an aspirin and then the fever goes away. Was the aspirin the cause of your fever decreasing? Well, it depends, right? That's a very difficult question to answer. But the implications are tremendous. think about in the 1960s, 1970s, when people were asking the question, does smoking cause lung cancer? Now, you think, well, this is such an obvious question. Well, back then it wasn't that obvious, right? You could see that there was a correlation between people that smoked and people that had lung cancer, the chances, the probability that someone had lung cancer. But have you considered all the possible variables in your model? Are people that smoked people in a special socioeconomical ladder or in a geographical location that increases the probability of developing lung cancer because of other issues in that environment? We don't know, right? There are many other possible explanations. So causality is obviously extremely important. This is a huge area of research. I'm only going to talk about it very briefly, but just to let you know that basically there are two ways to address this. There are two mechanisms by which people address this. The first one is by what's called causal diagrams. And that basically means graphs, right? And generally directed acyclic graphs. And this is basically a model, right? So this defines my model. And then once I have my model, I use symbolic language to answer or analyze, if you will, questions posed to these graphs, right, or diagrams. Okay. So causation may be defined as a variable x is the cause of y, say, if y, I'm going to use very loose terminology here, sees, you will also see people saying listens to, same thing, that there is a direct link between to x and determines its value in response to that, or to what it sees, right? Now that goes beyond everything that we have seen and everything, in fact, that we will see in the rest of the, because it means that you have to be able to go beyond, as I said, this model that I have, the probability of y given x, right, in probabilistic models. You have to be able to go one step further. This just defines a correlations, or the probabilities in that case, of the relationship between variables and their values, but it does not determine this, okay? Does not specify what the causation of y is. There's nothing wrong with this, but just machine learning per se, 99.9% of machine learning, which is f of x equals y, just cannot answer that question, okay? It just cannot answer the question of causation. Machine learning is based traditionally, as I mentioned day one, I think, AI, it's a big area, right? Artificial intelligence. And within AI, there's an area called machine learning. Machine learning is basically based on data, right? You give me data, and we have algorithms, statistical methods that we're defining here to extract information from this data and create models that are useful to me, right? Problem with that is that data by itself is intrinsically dumb, right? There's nothing intelligent about data. Data is just data. there's no knowledge, right, in there, unless I know something about the world that allows me to extract information from that model, right? So this is what people try to do. So to move beyond the classical model in causation models, people will define the probability of y given not x, but that I am able to apply something onto x, right? You will see many times this written as, this doesn't work, this. You will see this written as do x. And what that means is that you are working on x, right? You are changing the value of x to x. So the probability of y, given that I do something on x, right? I do some application on x. It's an action. There's also another thing that you can do. So this is an action. Another thing is counterfactuals. Okay. Counterfactual is what if, right? A what if condition. So let's see this very briefly with a simple example. So imagine this example here. I have x1. My first note, I'm just going to define this causal diagram first, right? And then we're going to go to the analysis. So you have x1, x2, x3, x4, and x5. This is the same model that we have used several times already. And I have these edges right here, okay? And let's say x1 specifies the season in my city. Let's say that the season can be dry or wet, okay? And just, we only have two seasons, dry and wet. During the dry season, it doesn't rain, and during the wet season, it does nothing else but rain, okay? Very simple town. Let's say that 2 is whether it rains or not, right? So rain can be yes or no. And this is whether, let's say I have sprinkles in my lawn and in my house, around my house, to water the lawn, right? In case it doesn't rain in the dry season. So this could be the sprinkles, and they can be on or off. And x4 is whether the ground or the area around my house is wet. So again, can be yes or no. And number 5 is whether the pavement is slippery or not, okay? Okay, so that's my directed acyclic graph, my model that defines these, the probability, or that can define the probability model that explains what happens. And now we can consider my second point here, which is what do we do with it? How do we extract causal relationships using some analysis, some intelligent analysis? So to do that, I can start asking questions. So for example, I could ask, if the season is dry and the pavement is slippery, did it rain? Right? So let's think about this. I'm actually asking the question. This is not an observation, right? I don't know that this happened. I'm just asking the question. This is the do, right? I do. If I apply the knowledge that the ground is, what did I say? I forget. If the season is dry and the pavement is slippery, right? So if this is yes, x5 means that the pavement is slippery around the house, but the season is dry, did it rain, right? So in that case, I would have this is D or yes, and this is yes, and this is yes, right? And now I can draw the equations of the probabilities that I have done before, right? Using this model. So the probability that it rains, given that x1 is equal to dry, right? And so on. You draw all the equations and you compute that probability, right? That's answering questions. So that's what this allows you to do. And by doing this, excuse me, by doing this, you're able to address problems of causality. So for example, possible answers. It's unlikely, right? We can compute this probability and we can determine that it's unlikely because the probability that x2 is equal to rain, meaning x2 equals yes here, given that x1 is dry and x4 is yes or no, whatever it is, right, is very low, right? Because this has a direct influence. If it's dry, the probability might be really low, right? Okay. But then, once you have answered your questions, you can follow with the second point, which is counterfactuals, okay? And with counterfactuals, you could ask, but if we check and find out, right? If I now go and check, I do again, and I find out that the sprinklers are actually off, right? So I go out in my world and I do a measurement and say, whoops, the sprinklers are off. And now I add this into my probabilistic model, right? Then what is the probability that it rained? Well, it's going to increase tremendously because although these two variables may be, if not independent, almost independent from one another at the very beginning, now they're going to be highly dependent based on these observations that I have, or observations and knowledge that I have added into the system. All right. So then you could ask the question, right? And I want to make this very clear because this is the problem with causality. So let's say that we go into the world and say, oh, sprinkles are off. So that means that the probability of rain has increased according to our probabilistic model given by this DAG. Then does this mean that the act of turning these sprinklers on, right? So that means that I do x3 equals on, right? I do that. Implies that it doesn't rain, right? Or that the probability of rain is small. Or if I go and do sprinklers off, then the probability of rain increases, right? So therefore, it's more likely that it increases, right? So you have to be very careful with that because one may be sort of true, but the other one does not need to be true. It's not generally true, right? The fact that I go out and I turn off my sprinklers doesn't mean that it's raining, right? It may mean that the grass is already wet, so I have enough water. Why do I, right? So obviously there is no relationship or no causal relationship between one and the other. Okay. Now to address these questions, another way to do that that you will see out there. Let me very briefly mention this. You will see something that's called functional Bayesian networks. And then here, basically, what we're going to do is at each of these nodes, I'm going to define a function, right? So I'm going to have this node right here is going to be determine its value. Let's say value C is going to be determined. Did I take the wrong one? The value C is going to be a function, is going to be a function, right, of this x1, right? I think it's not my markers. I think it's this whiteboard. It's so dirty that it just doesn't work very well. Okay. But if I come here, say I come down here, right? This one, let's call it, I don't know, D. This is going to be a function of x1, x2, x3, right? And so on. You see how this works. And then I can design a system of equations, of functional equations, and solve for that using the same method that we have defined. And that will allow me to define causal models using this functional approach. Okay? Questions? One more application of all this. This is all I'm going to say about causality, because this could be a whole course by itself. But I do want you to know that although this is not common in machine learning, that these models do exist, and people are working on them as we speak, and hopefully will become more popular in years to come. Another final application I want to mention about Bayesian, the Bayesian models that we have discussed, it's what's called the naive-Bayes classifier. So all these methods that we have derived thus far can be used now to derive a very simple, very straightforward, but very powerful classifier called the naive-Bayes classifier. And to do that, as always, we start with the feature vector x of, say, p dimensions in the real domain. So we have xi equal x1, or actually xi1 through xip, right? And we are going to add a latent hidden variable, as we so commonly do, which is going to be zi. It's equal to zi1 through zic, where C is the number of classes. And my Zij is equal to 1 if my vector xi is a sample drawn from the distribution of class, what did I say, J, and 0 otherwise. Right? This is how we've defined these things before in these graphs and in other models. So note that I can draw this as my xi, right? Or xij even, let's say, it's specified by my vector here, Si, right? Oops, Zi, excuse me. Zi, right? Or you could say xi1 to xip, is that what I say? Yeah. To xip, right? And Zi is the one that determines or has an influence in their value, right? So that's just a graphical representation of what I have drawn there. And from this graphical representation, we can compute the probabilistic model, right? The probabilistic model of x given, or xi given Zi is equal to what? It's equal to the product of the probability of xij given Zi for j1 through p. Correct? Right? So far, so good. And now, if I want to find the class of a vector x, right? My classifier is going to be equal to, let's see, it's going to be, I want to maximize this value, right? I want to find the maximum probability. I want to find the class for which a vector x has most probability of belonging to, right? So how am I going to do that? Well, I'm going to maximize this. So I'm going to find the maximum of, I'm going to add the prior here, the prior of each class, the product of j from 1 to p of the probability of xij given Zi, right? And I want to find the I that maximizes this and then take the argument, right? And that is going to give me the class that maximizes my model, right? That's it. This is the naive-based classifier. It's really simple, straightforward to implement. And you will see used all the time, at least as a baseline classifier, right? Because it's just so straightforward to compute. You'll see most of the time that people will compare their own algorithms to this naive-based classifier. Very simple, very useful classifier to have in mind. Okay, I'll leave it at this. I think this is plenty for Bayesian networks. And I want to move on now, unless there are any questions, to Markov models and hidden Markov models. Any questions about Bayesian networks and DAGs? Now make sure that you do all the readings that are available in Canvas, right? Download the papers, the book chapters, read everything that we have covered today. If you need to rewatch the lectures, rewatch the lectures, right? They're all on YouTube. Because after today, well, maybe today or maybe Thursday, but after this or next lecture, then we're going to go really fast covering a lot of very powerful material, right? The material that you're most likely to use at the end of the day. But all that material is based on everything that we've covered thus far. And if you're not extremely familiar and hands-on with this stuff, you're going to get lost, I mean, like that, right? It's instantly. You need to know all this terminology, all these methods to be able to understand the more advanced machine learning algorithms, all right? Okay, so since I don't see any hands for questions, I'm going to use the slides for this because we're running out of time in the class, unfortunately. I want to make sure that we have time to cover at least briefly, but we can cover all the topics that I said we were going to cover. So I'm going to use sporadically. I'm going to use the slides. I know it's not the most ideal way to cover certain topics, but I'm only going to use them when I know that you already have all the knowledge, or you should have all the knowledge if you review all the papers and lectures that you need to understand this. All right, so Markov models and hidden Markov models is just one other type of graphical models that I want to cover in this class. Let's start with a Markov model. Markov model is nothing else than a stochastic process. The output of the model is a set of sets. So we have the states. The states are going to be defined by nodes in our graph. So each node now is going to determine or specify a state of our model. And this state corresponds to physical observations, okay? And the probability of being at the state, say, I at time t, depends on previous observations, okay? That's the basic premise. Now, in Markov models, it is typically to simplify the probabilistic model by assuming that the probability that I'm at the state, say, where's it here? State j at time t, right? It only depends on the probability that I am at a state si at t minus 1, okay? So that means that I am not taking into account everything that has happened over time. I'm only taking into account what's happened just a second ago, okay, in my previous time period. Now you can go to second order, third order Markov models, which keep considering more and more. Now this is different from what we've seen in Bayesian networks, right? Bayesian networks are specifically ideally designed for causal models, right? This is how I define the physics of the world. This is how the world works. Markov models are better defined by time, right? These are variables that depend on time, okay? This is very different from what we had in the Bayesian networks, right? Where we didn't talk about time at all. I just say whether the ground is wet. Does this mean that it rained, right? I mean, this is just observations at this period in time right now, right? Doesn't mean that what's going to happen or what did happen or what didn't happen, right? It's what's happening right now. That's the interest. But here we are considering time, and that means that obviously what is happening now depends on what happens before now, and that means all of before now, right? To eternity or to the Big Bang, maybe, or even before that, if there was a before. But obviously this is just too complex, so we're going to say, okay, I'm going to just take the previous step, okay? And since we discretize things, that's how we're going to define. So we're going to define these variables, aij's here, right? They're the transitional variables. What's the probability from going from I to j, okay? Which is given by this, so that I'm going to be at the state j at time t, given the fact that I know I'm in a state I at t minus 1. Let's say that I have n possible nodes. And obviously, all these probabilities, all these transitional probabilities have to be positive or 0, right? There could be a 0 probability I'm going from I to j, but there cannot be a negative probability, obviously. And all the probabilities, when I sum over, say, j, have to add to 1, because in my model, if I'm at the state I, the sum of all the transitional probabilities that I can go to all the different places has to be 1, because next step I'm going to be somewhere, right? I cannot be nowhere. So all the probabilities have to add to 1. Okay. So it's just a graphical representation of what I just said, right? So if node S1 is right here, right? And the probability of staying at 1 is A11. The probability of going to S3 is A13, and so on. So you see how this works. And this is very useful to address a variety of problems. This would be a stochastic, what you have seen in stochastic processes in 6001, right? This is a classical model that you can design with this. Say that you want to model the weather, right? And the weather can either be rainy or maybe snow. It can be cloudy or it can be sunny, okay? And so let's say S1 we're going to define as rain, S2 clouds, and S3 sun. And then what is the probability that the transitional probabilities, which I have here as a matrix, of going from 1 to 1? Well, it's 0.4, right? So this is something that based on history I can measure, that in my town, the probability that if it's raining, that it'll be raining tomorrow, it's 0.4. But what about the probability that it's going to change? Actually, I'm going the other way, right? From here to here, it's 0.4. But what happens if, what's the probability from going from rain to just clouds? 0.3. And from rain to just sunny, it's 0.3 again, right? And so on. So this how this works. And then with this, we can answer a lot of interesting questions, right? So for example, we could ask, what is the probability of having the following observation, that today is going to be sunny, the next day sunny, the next day rainy, the next day rainy, and then sunny again, right? And that's very easy to compute because I can start with the prior probability that today it's sunny, right? It's the probability, the prior probability that it is. And then the transitional probability from 3 to 3, from 3 to 1, from 1 to 1, from 1 to 1, 1 to 3. And I do this multiplication, I get an answer, right? Now, I can ask other questions like if I knew, let's say that I knew that yesterday was sunny, then the probability of the model is such and such, right? And in that particular case, with the numbers I gave you, it would be 3.072 by 10 to the power of -3, right? So tremendously small. You're going to observe that sequence in that town, hypothetical town. You could ask other questions. For example, which is the expected number of days? That means the duration, right? How long it is going to be to stay in a specific state, right? And that's obviously a binomial distribution, right? So you're going to compute the probability of staying at this state AII d minus 1 times, right? And then transitioning to some other state that's not I, which means 1 minus A11 is the probability that I'm not staying at AII. And that's equal to this, right? So now you can compute, for example, the expected number of consecutive cloudy days, 2.5, right? In Columbus, in the winter, it should probably be like 30, right? Something like that. Or 90, the whole winter. So this is how these things work. But these are only useful up to a point. Because in reality, the problems that we want to model in the real world are much more complex than this, okay? Or most of the problems in machine learning. Because these are very straightforward models, right? That I can model, we know how to do this. This is relatively easy. But in many of the real world problems, what you have is what's called a double stochastic process, okay? So let's see how we can define this. In a double stochastic or double embedded stochastic process, what this means is that my observation is not directly an observation of the variable that matters, right? The variable that matters is a latent variable, as per usual, right? We should be very familiar with this by now. It's a latent variable to which I have no access to, okay? I can only see my variable x, but my hidden variable, the latent variable z, right, is hidden to me. So let's define this with a very classical problem. So imagine, this is called the urn and ball model. This is very classical. So imagine that you have different urns or boxes, right? I have n urns. And in each urn, there is a percentage of red balls, blue balls, green balls, yellow, orange, and so on, okay? Now, I could go here and say in front of you and say, okay, I'm going to select urn number 2. I'm going to pick up a ball and it's red, right? And then I'm going to go to urn n. I'm going to select another ball, it's green. And then I'm going to come to urn 1 and select another ball. So when I do this process, right, you can start computing the transitional probabilities of me moving from 1 to 2, 2 to 3, or 1 to 3, and so on. And the probabilities I extract certain colors of balls in each urn, right? All right, so far so good. So that's a simple Markov model, right? I could do that. I know how to do this. But now this is what I'm going to do. I'm going to put a wall in front of these urns, okay? It's a shallow wall like this, and the urns are right here. You can see me, right? But that's all you can see. And you probably don't even know how many urns I have, right? You certainly don't know what's the percentage of colors in each of the urns. And then all I'm going to do, based on some hidden function that you don't have access to, right? Sounds familiar. It's a hidden function that I use to determine which urn I select. When I have selected that urn, I pick a ball, and I showed you the ball, right? So all you see is the color. And you see red, green, green, blue, red, orange, yellow. And you go like, whoa. All right, what just happened behind the wall, right? How can I now model this? This we can model with a hidden Markov model. So this is what the model is going to be like. We're going to have the transitional probabilities, right, that I need to know to interpret this observation that I just observed, red, green, green, blue, orange, yellow, right? To interpret this, I need to know the transitional probabilities between these urns. I need to know the probabilities of extracting a specific color at each individual urn, and I need to know the prior probabilities, okay? This is what determines how I do this selection and what type of observation you're going to get. All right, let's call this B, BJK, right, which is the probability of observing VK at time t, knowing that at time t I'm at state Sj. Okay? And again, this is nothing else than the prior probability of being at state I. All right, so there are three problems that I want to be able to address. Three problems. Problem number one, given an observation, right, what I showed you, red, green, green, blue, orange, yellow, given that observation and the model, right, so you have the model, I've given you the model, the underlying function, I've given it to you. How do you efficiently compute the probability of that observation given the model? Okay. All right, we'll address this first. This is the easy question. The second problem, which is called recognition, given an observation sequence and the model, how do you find the sequence Q which best explains the data? Okay. So it means, again, I'm in a graph, right? And I give you a set of observations, red, green, green, blue, orange, yellow. And now I ask you, which is the sequence of states, Q, right? Si, Sj, Sk, Sl, and so on, that I went through to obtain that observation. What is the most likely sequence? Okay? That's a much harder question to answer. And finally, problem three, this is the main question, but the most difficult one is, how are we going to learn the model? Because the model is not given to us, right? At some point, we have to create the model, to build the model. So let's see this one by one. Problem one. This is trivial almost. So consider this. I have this observation sequence, right? O is equal to O1, O2, say up to O capital T. All right? To get this observation, I went through the sequence Q, Q1 through Qt. Okay? So the probability of having or observing O, given that I went through that sequence, given my model, is nothing else. Now let's see. It's a probability at time t of observing OT, right? Given that I'm in Qt and given the model. And I have to multiply this for every single state I go through, right? So this is the product of all these probabilities, correct? Or I can write it like this. This is nothing else. This should look familiar by now, right? I can write this as the sum of, and this is now, I'm going to consider all the possible Qs, right? All the possible sequences that gives me that observation, right? So this equation here can be expanded as the probability of O given Q and the model times the probability of Q given the model, right? Right? What is the probability of actually having this sequence, Q, any sequence, given my model, right? Okay, so now I sum over all the possible sequences I can go through that are going to give me that observation I just observed, right? So I do this, and this would be equal to the prior probability that I start at Q1 times the probability that Q1 I observe O1, right? Times the transitional probability of 1 to Q2, and observing O2 one time at Q2, and so on, for all the possible sequences that are possible in that graph, right? That's that simple. That's my model, my probabilistic model in that graph. Now, this is trivial, but it's computationally expensive, right? If I have to compute this like this, the complexity of this algorithm would be 2t, t, remember, it's the number of observations that I have, times n to the t, where n is the number of states. Obviously, if n or t or both are large, this is uncomputable, right? At least in a finite amount of, or it's, by finite, I mean, in our lifetime. Now, we can compute this in 300 years. To me, it's like, it's not finite. So how can we make this more efficient? To do that, I'm going to define what we call the forward variable, okay? So we're going to define this variable alpha 1 of I, okay? See what alpha 1 of I is. Alpha 1 of I defines the probability, the prior probability, because I'm at 1 time t equal 1, right? That I start at this state I, and that once I'm at this state, I observe my first observation O1, right? Okay, and I compute this for all the possible initial states, right? All the n possible states. And now I do a for loop here, and in this for loop I compute the forward variable for the next step in time. And what's this going to be? It's going to be that at time t plus 1, I'm at the state j. Okay? So forget about this first component first. Let's look at the second one. It means that I observe OT plus 1 once I'm at the state j. Okay? And how can I get to state j? I can get to state j by going from I to j, right? Times the forward variable that I was at I to begin with. And I have to add over all the possible i's I can be at, right? All right. And what's the final variable right here of my model? It's nothing else than the sum of all the possible final forward variables, alpha capital T. Okay? You have it here in a graphical representation. Each forward variable represents nothing else than the probability of being at Sj at time t plus 1, right? Which is given by all the summations of if I were at S1, then what's the probability of me moving to Sj? If I were at S2, what's the probability of moving to Sj? And so on, right? So that's a forward variable. By doing this, this is just another way of representing this. By doing this, I can also do the backward variable. Backwards it's the same thing, but now I start at the very end. So the backward variable is actually going to be equal to 1 at time t, right? Because probability that I'm at the end, well, it's 1. And then what I'm going to do exactly the same I was doing, but reversed. So now to go to step t, I'm going to do the transition from I to j, right, times the probability of observing t plus 1 at j times the previous backward variable, right? So now this does from the previous state to the next to the previous state, right? I'm sorry, not next, before the previous state, right? And so on. And I keep going backwards. And these two algorithms, either you can use the forward or the backward, doesn't matter. These two algorithms simplify the computation of the probability of the observation given the model to n squared times t, which is still a large number, but at least it's n squared. It's a polynomial. It's not an exponential function. So much less computationally expensive. So this is problem 1. That was the easy one. Now, how about problem 2, which is called recognition? It's called recognition because you have to reconstruct. You also see reconstruction sometimes. You have to reconstruct the sequence that I go through, okay, to give you that observation. So I give you an observation, but you didn't see my sequence of urns. You have to tell me which sequence of urns am I most likely have I used, right, to give you that observation, right? Well, this does not have a solution unless we define what do we mean by best or optimal, if you will. What's the optimal sequence? We have to define what that means, right? As always, remember, I've said that already maybe a couple times, maybe more. Optimal by itself means nothing, right? And you keep saying people, oh, this is the optimal result. The optimal. There's no optimality, doesn't mean anything unless it's with respect to some criterion, right? So that's what we need to define. What is our criterion that we want to use? So for example, we can say, find the individual states that gives the highest probability for each particular observation, right? Meaning that I'm going to select the states, right, for my sequence that maximize the probability of each of the individual observations, each of the individual balls. So if I know that urn 1 mostly has red balls or just red balls, every time I see a red ball, I'm assuming that you are at S1, right? That could be a criterion. Unfortunately, that does not consider the transitional probabilities, right? So we may want to consider transitional probabilities. Ideally, I want to consider all the transitional probabilities together. So let's do that. I could do triplets. I could do quadruples. I could do all of them. I'm going to use all of them. So this is the most common solution, to find the path that maximizes all the observations using all the transitional probabilities. And the algorithm that does this efficiently with the forward and the backward algorithm, it's a Viterbi algorithm. Viterbi, it's a person that did his studies at USC. And with these ideas of graphical models, decided to start a communication company that you might have heard of called Qualcomm. Became a billionaire. Came back to donate, was it $100 or $150 million to to his department, EC department at USC, and now it's the Viterbi Department of Computer Science and Engineering, whatever it is, right? So please take this knowledge, go out there, become a billionaire, then donate a couple $100 million to our department, and we'll change the name for you. Okay. All right. So let's see how this algorithm works, which is fundamental in communications. It's fundamental especially for cell phone users, right? When you have, or the internet, right? You have to find a path, the most appropriate path to send a communication signal, right? Obviously, these algorithms are very powerful, very practical in communications. So this is how it works. Let's only look at the deltas for now. Okay, let's start with the deltas. So at the initial state, at time t equals to 1, what is the probability that I'm at a state I? Well, we know what it is. It's a prior probability that I start at the state I times the probability that you observe O1 once at this state, right? So these are all the prior probabilities given my observations. Now forget about this one, okay? Now, what's the next step? The next step is, again, forget the max. It's going to be the previous delta, right? So let's say if I only have delta 1, the probability that I started at I, state I, then I transition from I to j, and then I observe O2 once I'm at j, right? And I can do this in recursion. I can keep repeating that. And obviously, at each step, what do I want to find? I want to maximize, right? Up to that point, what is the best way to do it? Okay, so these are all my deltas. And to do that for, note, I do that for all the possible transitions to all the possible states. Okay, I'm actually computing all of them. And then finally, what am I going to do? I want to find the maximum of the final delta, right? The one that maximizes the probabilities. So that is obviously the solution that maximizes the probability. But what is the sequence that I have used to maximize this probability? Okay, we start with that sequence empty, right? I don't have anything. At the next step, what I'm going to find is I'm going to use this probability right here, right? And now what I'm going to do, I'm going to take the argument of that, meaning the state, right? And I'm going to keep that state Sj, right? And, or Si. And then at the end, what I'm going to do, the full sequence is nothing else than the argument that maximizes the final delta, which I can find as this recursion here, right? The function at qt minus qt plus 1, right? So I keep track of which state maximizes the probability that I have computed. Very simple algorithm, very powerful. Problem 3, and because it's based on this forward-backward idea, right, that we have discussed, it's very efficient. All right, final problem. By far the most challenging, obviously. The main issue with this is with estimating or coming up with the values of that model is that it doesn't have a solution. Okay. Now, to understand this, let's see if we can understand what a hidden Markov model really is. So let's consider a hidden Markov model that only has one state, S1, okay? Just one state. And then for each possible observation, I have a probabilistic model, right? The probability, right? So in the simplest case, with the balls, it's the probability of being red is 0.3. The probability of blue is 0.2, and so on, right? It's just a simple number, right? But with more realistic, I mean, this is not the problem you're going to model down the line, right? Is it? If not, life would be really nice. So the most classical case is you're going to have a probabilistic model that's much more complex than this. Let's say that you are going to model these probabilities of each event occurring in just one state, S1, right, as normal distributions, right? So the probability of, say, observing a specific object, right, is going to be given by the normal distribution N1, okay? And the second object, N2, and so on, right? But I can go even further than this, right? You can create more complex or more precise models of my underlying distribution using, for example, mixture models, right? So now a mixture model in each state is going to give me the underlying probability of observing every single object or class or what have you in my problem, right? So what's a hidden Markov model? A hidden Markov model is nothing else than a mixture model when I add time to this, meaning that this mixture model changes shape over time. Depending on the state I'm at, this mixture model varies, right? Now, that means that I have to estimate the parameters of my mixture model at each state plus the additional transitional probabilities, right? Now, do we have an algorithm to estimate this type of parameters? Yes, speak up. Very good. Yes, the EM, or expectation maximization algorithm, right? It's exactly the algorithm we're going to use because it's the same problem. And Baum-Welch is how people sometimes call it in hidden Markov models, but it's nothing else than the EM algorithm. And this can be computed using these variables that I'm going to define here, these psi variables here, which are the probability of being at the state Si at time t and Sj at time t plus 1. And then remember that that means that I can use the forward variable to determine what's the probability that I'm at the state Si. I can use the backward variable to determine that I'm at state Sj. And then in between these two, I have the transitional probability of going from I to j and the probability of observing that OT plus 1 once at j. Okay? And I normalize this by dividing it by the probability of my observation given the model, right? Okay? All right. So with this, I can compute the different parameters that I have in my model. So look here. Start with the prior probabilities. That's easy. Here, all you need to know is the expected frequency. That means the number of times I'm in state Si at time t equals 1, right? So given a certain number of observations, I can just compute those priors. That's easy. Okay. Now how about the transitional probabilities, Aij's? This would be the expected number of transitions from a state Si to Sj divided by the expected number of transitions from that state. And that we know is this variable right here that we just defined, right? Given all the possible transitions at any single time that I can have from 1 to t minus 1, and divided by this normalizing value here, which is the expected number of transitions from that state, right? That means what is the probability that I'm already at that state? Okay. So that takes care of two variables already, two parameters of my model. How about the probability of observing OK once I'm at, or an entity, excuse me, OT equals to K once I'm at the state J? That would be the expected number of times in a state J that I observe my symbol or my object, Vk or K, divided by the expected numbers that I'm in that state. Okay? And this is given by this value here, which means that I'm at that state t, but that I observe, right, that Vk is actually my observation at that time, divided by all the possible times that I'm at that state, right? So if I'm at the state Sj 3 times, and one of these 3 times I observe red, then the probability of red here for that particular state is 1 over 3. Right? That's simple. All right. The trick is to use the EM algorithm to iterate this, right? To keep iterating these different variables to compute the expectation and the maximization to come up with the model. Okay? And I've added in Canvas details of the algorithm and a paper that goes through all the derivations carefully. Now remember that the EM algorithm does not give us the maximum likelihood estimator. It only gives us a local maximum or local minimum, depending on what we're looking here, local maximum, right, of our function, because it uses gradient descent or gradient ascent to find that minimum or maximum. Okay? So there are limitations to the problem. We can iterate this many times, as we said, with mixture models. We can use genetic algorithms to improve it. We can use prior knowledge to improve the model, and so on. Okay? Another extension of hidden Markov models that you may find useful is what's called coupled hidden Markov models. The idea here is, imagine that you are designing a model that has intrinsically that has independencies that are intrinsic to the problem, right? If you have independencies, you can separate this into two hidden Markov models, right? But what happens if these two different models are dependent of one another? Then what you end up with is something like this, where you have your observations, your latent variables that you don't observe, right? Or vice versa. And then you have dependencies that are specified here by these edges that are connected to another hidden Markov model, right? So, for example, you could define a hidden Markov model of your behavior, right? Of what you're going to do or how you walk from here to the door, right? And then you could have this same model repeated for each individual, assuming we're all exactly the same. But then they interact with one another, because if we go all at the same time toward the door, right, then there are going to be dependencies on these variables, right? And those have to be modeled. And it's easier to do this by coupling these hidden Markov models rather than just trying to put everything together in a single model, right? Because the number of variables that you need to estimate with the EM algorithm, it's much more controlled. These are other ways of defining the models. The classical application of hidden Markov models is in speech recognition. That used to be the most classical way of addressing speech recognition until deep networks came along for speech recognition very recently, in just the last few years, maybe 3, 4, 5 years. Hidden Markov models was the algorithm to go. Okay, you will see still being used alongside deep networks to do speech recognition to this day. Sign language as well, modeling DNA. This is a very classical application of hidden Markov models. All right, that should be it. Any questions? All right. The next topic, can someone get the lights? The next topic is going to be non-parametric estimation. So up to now, I'm only going to summarize this very quickly, and then we're going to cover this in more detail in our next lecture. So up to now, we have assumed that our functions that we are learning, right? Remember, we are in the probabilistic approach, right? So we're defining probabilistic models that explain how our world behaves, or our data. And nonparametric models is exactly the same, but the probabilistic models that we're going to define, right? The probabilities of our variables, our probabilities of y given the variables, and so on. All the different types of probabilities that we have modeled, right? That we have used to define, what have we used them for? Factor analysis, probabilistic PCA that I mentioned, all the density estimation, all the mixture models, either Markov models, Bayesian networks, right? All these different models, all these different algorithms that use probabilities, up to now, were based on distributions like the normal distribution, say, right? That are given by a certain number of parameters, right? And this is ideal. It's ideal because if I do assume that my underlying distribution is a normal distribution, then all I need to do is estimate the mean in the covariance matrix, right? And if I assume it's a Laplacian, all I need to do is to estimate the B parameter, right? The pickedness, if you will, of the distribution, right? The skewness, and so on, right? It's very attractive. That's why we use parametric models. But what happens if our underlying distribution is so weird that these parametric distributions are far, far, far away from the reality? Well, then we turn to mixture models, right? That's why we introduced mixture models. And that's indeed one way to address the problem, okay? And it's the most common way to address it. But another way, which is also common, not as common, but it's also used, is using non-parametric methods. And there are two basic ways to do that. One is called Parsons windows, that we're going to see first, but it has its problems. And then second, one that sort of addresses these problems, which is the most common one, which is called the k-nearest neighbor algorithm. And that is like the algorithm that you're going to use most often to define things non-parametrically. And as we saw today, the naive Bayes classifier, and that is being used as a baseline classifier to compare everything you're going to do to. K-nearest neighbor is like the baseline estimation, density estimation algorithm that you're going to use to compare it to anything else that you do as well. Okay? All right, I'll do that next time. See you then.